Okay, so in the remaining time, what I would like to discuss is kind of, let's say, the condensed matter physics, the applications of quantum mechanics to condensed matter physics, and in particular, the band structure. Now, what we will be eventually studying is, I mean, if you have a lattice for a crystal is basically, you can just treat it as a I mean, you have some structure where the atoms are located, the nuclei are located. So it goes to infinity. It's basically a periodic structure. So that is what we will be first studying. What happens if you have a periodic potential? And the simplest one we can imagine, the simplest periodic potential would be, I mean, one we can actually solve. You can take the infinitely many Dirac deltas in one dimension, separated by the same distance. Now, we had already studied, let's say, one Dirac delta potential, and we had seen that there was a single bound state. So first, let's see what happens if we have two Dirac deltas. Then we will eventually try to generalize some of the things that we have obtained, some of the differences, some of the changes that arise when we go from one Dirac delta to two Dirac deltas, and then 3, 4, and infinitely many Dirac deltas. So this was the general scattering solution, let's say, in the Dirac delta potential. Let's just assume a potential of this form, lambda Dirac delta x minus a plus lambda Dirac delta x plus a. So we just have, instead of one Dirac delta, we have two Dirac deltas separated by a distance 2a, and we chose the origin to be their center. So if you just put it in the scattering solution, we get psi 0, psi x. This is equal to psi 0 of x minus I m over k, and lambda times e to the power I k a, psi of a, plus e to the power I k, absolute value of minus a, psi of minus a. Or since we have assumed that a is a positive number, this is equal to psi 0 of x minus I m over h bar times lambda e to the power I k a, psi a, plus psi of minus a. This is our psi of x. No, sorry, I had a mistake. E to the power I k. This is x minus a, absolute value, and this is absolute value of x plus a. So now you see we have these two unknowns. We don't know what psi of a is. We don't know what psi of minus a should be. We have to kind of solve for them. What we can do is, I mean, since this equation is valid for any x, we can just choose x to be a and x to be minus a. So that gives us two equations for the two unknowns, and we can solve for them. So let's see, psi of a should be equal to psi 0 of a. You see psi 0 of a, at least in the scattering one, this is our incident wave. We are just sending one plane wave and see how it evolves. In the bound state problem, we will eventually take the k to be purely imaginary, and psi 0a will be 0. But before that, we have to find the point where the scattering amplitude diverges. Psi a will be psi 0 of a minus I m over h bar lambda psi a plus e to the power 2 I k a, psi of minus a. This is one equation we have. And now we have psi minus a, which is equal to psi 0 of minus a, minus I m over h bar lambda psi a times e to the power 2 I k a plus psi of minus a. So these are the two equations we have for the two unknowns. Let's first choose psi 0 to be psi 0 of x to be e to the power I kx. This is our incident wave. So psi 0 of a is equal to e to power I k a, and psi 0 of minus a, this e to power minus I k a. Now let's just rewrite these two equations in a slightly different form. We have psi a, psi of minus a. This is multiplied by the matrix 1 plus I m over h bar lambda, and I m over h bar e to power 2 I k a. This, and also lambda. This is the first line. And for the second line, we have lambda I m over h bar e to power 2 I k a, and 1 plus I m lambda over h bar. This would be equal to psi 0 of minus a. Now we can just solve for psi 0a and psi 0 minus a, or psi a and psi minus a. This will be equal to, well, the inverse of this matrix. Well, we will not proceed any longer. You see, what we will eventually want, you see, we have this solution. And so psi of x, this is equal to, for x much, much larger than a, away from the scattering solution. This is psi 0 of x minus I m over h bar lambda e to power I k x, psi of a plus psi of minus a. And eventually what we want is the poles. If you remember how we identified the bound states, we just first said k goes to I times kappa, and then we said f as a function of this kappa should be divergent when kappa is equal to the bound state energy, bound state wave vector, not the wave vector but the k. So this is how we identify the position of the poles. Now, if you look at this expression over here, we know what our f is. F is equal to minus I m over h bar lambda psi a plus psi of minus a. So if, this diverges. Now, when f diverges, then we have a pole. Then we have a bound state. Now, this is our f. So for f to have a eigenvalue, a bound state, f should diverge. Now, when does f diverge? You see, these are our functions, let's say. M inverse psi 0a, psi 0 minus a. Well, psi a or psi minus a diverges if M inverse diverges. M inverse diverges when its determinant is 0. So we can identify the poles by taking this matrix M. No, this is our M, not M inverse. We take this matrix. Instead of k, just substitute I times kappa, but that brings me minus 2i kappa, and here also minus 2i kappa times a. Did I forget one thing? Yes, this is not h bar, this is k. So k goes to I times kappa. So this is kappa. I doesn't appear. I have a kappa. This is kappa. When this determinant is equal to 0, then I know that I will have poles. Well, let's calculate that determinant. We have 1 plus m lambda over kappa squared minus lambda squared m squared over kappa squared times e to the power minus 2 kappa a minus 4 kappa a. This should be equal to 0. Or 1 plus m lambda over kappa squared. This should be equal to lambda squared m squared over kappa squared e to the power minus 4 kappa a. Now the question is, how many solutions do we have? Let's say this is as a function of kappa. First the left-hand side. The left-hand side, when kappa goes to 0, it diverges. When kappa goes to infinity, it goes to 0. So it looks something like this. This is the left-hand side. Yes, it goes to 1. Now the right-hand side, when kappa goes to 0, it again diverges. Now one question, when kappa goes to 0, the right-hand side is below or above the left-hand side? They both diverge. But if the overall coefficients, they are both proportional to m squared lambda squared over kappa squared, but the right-hand side has this additional e to the power minus 4 kappa a, which makes it a bit smaller. So it starts when kappa is close to 0, it diverges, but it is smaller than the other one. Now when kappa goes to infinity, it goes to 0. So if this is the shape, there are no poles. So probably we made a mistake somewhere. Let's check our calculations.
Actually, so a minor mistake, but I don't know. Right-hand side at all. And before that, the phase factors in F and the equation above.
This one.
The last line.
This one.
Yeah. There should be, I guess, an additional e to the minus I cubed. I mean, in front of.
As you see, a is negligible. In that limit, this is correct. Now, this is either we made a mistake, or the actual shapes might look like this one. Nope, sorry. I would expect this thing. I would expect 2 poles. You see, when A goes to 0, we should have 1 pole, at least. That we already know. So we probably missed some factors over here. Anyway, I will not spend that much time on that. But at least when A is equal to 0, we have a single Dirac delta, and we already know the solutions, etc. So here we should have this behavior. So the two sides intersect at 2 points. here, and here. So now what happened? So basically what will happen? So we have one Dirac delta over here, another one over here. Now, first of all, if they are very, very far away, we have degenerate states. So at degenerate states, when A goes to infinity, it's basically this square over there. We have a double pole. Now, if we have a double pole, probably the mistake, oh, sorry, we don't have a mistake. But you see, lambda is a negative number. That is what we had forgotten. Now, since lambda is a negative number, as, let's see, as k goes to 0, the left-hand side goes to minus infinity. No, sorry, not minus infinity. There is a point at which the left-hand side is equal to 0. There is at least one k for which the left-hand side is equal to 0. Okay, so there is at least one k for which the left-hand side is 0. Okay, it doesn't go, probably it doesn't go above 1. It approaches 0 below 1. So this is 1. Okay. So we have these two poles. Because lambda is less than 0. So this is what's actually happening. If you have both of these Dirac deltas infinitely far away, you have two states, each one localized at one of the Dirac deltas. Basically, they are degenerate because they are infinitely far away. And so you can just imagine that you have a 2 by 2 Hamiltonian matrix. Epsilon, epsilon, 0, 0. This is when A goes to infinity. You have two degenerate eigenstates. Of course, you can just take any of their superposition and you will still have degenerate eigenstates. Now, as these are approaching, what happens is if you start with a particle localized in one of the Dirac deltas, it can basically tunnel into the other one as the distance is approaching. As the distance, if the distance is not infinite, there is a finite tunneling probability, and hence the particle can tunnel from the left Dirac delta to the right one and back and forth. So that basically means that in this effective picture of 2 by 2 V, there is a perturbation which will allow the first state to make a transition to the second one, and the left state to make a transition to the right state, and the right state to make a transition to the left state. And so the new H, which is epsilon delta delta 0 epsilon. Now the new eigenstates will be 1 minus 1 and 1 plus 1. And the new eigenvalues plus minus, this will be equal to epsilon plus or minus square root of, well, let's say it will be plus minus something of the order of delta, if delta is small. So what happened is we had initially a single state, let's say two separate states, degenerate. As we are bringing them closer together, these states, they split into two. Why two? Because we started with two Dirac deltas and we still have two states. For each one of the initial states, they still exist, but they are kind of slightly shifted. Now, to see what will happen if we have, let's say, 3 Dirac deltas, well, you see the pattern of this matrix is kind of nice. The diagonals are all equal, 1 plus m lambda over k. The off diagonals will correspond to lambda m over k times e to the power minus kappa times the separation of these 2 Dirac deltas. If we have 3 of them, now you see this first, you can just imagine that the first state is a Dirac delta in the first one. The second state the first state is localized in the left Dirac delta, the second state is localized in the second Dirac delta. And so this off-diagonal matrix elements are basically nothing but their overlaps. If you calculate their overlap amplitude, it will be proportional to e to the power minus 2 kappa times a, because that is their separation. Now, if you had 3 Dirac deltas, then we would have a 3 by 3 matrix, and the third entries would have terms like e to the power minus 4 kappa a, e to the power minus 2 kappa a, depending on the separation of the states that are corresponding to those states, let's say. And the solution, we would need to calculate a similar determinant. And so we would have 3 states, 3 eigenstates. If you would have 4 Dirac deltas, we would have 4 eigenstates. And with the addition of each Dirac delta, these states, initially they were degenerate. Now we add 2 of them, we bring them together, they split. If you add a third one and bring it closer, it will cause, if you have 3 of them, then the 3 of them will split. If you have 4 of them, well, you start with 4 states, and when you bring them closer together, you will have 4 split states. Then you can have 5 Dirac deltas, 6 Dirac deltas, 7 Dirac deltas, 8 Dirac deltas. And you will have many states. Now, the energies will not go to infinity. The energies will be still within a range, but you will have infinitely many states if you have infinitely many Dirac deltas. So this is basically what we call a band. So here you have a range of energies. Within those energies, the energies can take a continuum of values, but they cannot take values out of that range. Now, the same phenomena happens in solid-state systems. In the solid-state systems, of course, we don't have the Dirac deltas. We have the atoms, and the atoms all have many states. And when you bring many atoms together, each one of those states, they split. And each one of those states will form a band. They might split. Okay, various bands might start to overlap, etc. Now let's try to solve this problem for the infinite Dirac deltas. Now, of course, you can just take this one, this 2 by 2 matrix, write it as an n by n matrix, and try to solve it for a general n by n matrix and take n to infinity. But let's do it some different way. Now let's first just assume a periodic potential. So basically we have a potential such that if you just shift it by some number, let's call it A, it is equal to itself. Now the Hamiltonian of my system, I'm just considering a single particle, is again p squared over 2m plus v of x. Now let me define the translation by A as you just act it on any function of x and it gives you f of x plus A. Is this conserved? Is this a symmetry of the problem? Now in fact not just a single A, you can define t n times A to be equal to Ta to the power n and t of minus A. Yeah. ta to the minus 1 is equal to t of minus a. So what would we expect this commutator to be? 0. Does Hamiltonian change if we translate our system by A? Nothing changes. Yes?
So translation, when you add x by a, it's and in the lattice you move from one to another point, so when you take to the minus 1, does it move?
You just go in the other direction. And you translate by A this way.
Okay, minus a opposite.
Minus a in the...
Minus, it is a minus.
Well, you see t of NA, t of MA, this is equal to t of n plus m times A. Do you agree with this one? You just translate by n, then translate by m. Then t of A times t of minus A, which we said that this is t of A inverse, this is identity, which is t of 0. Yeah, basically these form a group. So it satisfies all the group properties. It has the inverse, etc. You can translate toward the left or translate toward the right. If you choose one of them to be translated by a positive multiple of A, the other direction just becomes translating by a negative multiple of A. Okay, so now we have an operator which commutes with our Hamiltonian. Let's say TA. So whenever you have an operator that commutes with the Hamiltonian, what do? You try to diagonalize both of them together. Now let's see. Let's try to find an eigenstate of TA. This is equal to, well, if it's an eigenstate, then it should be some lambda times psi of x. But from the definition of TA, this should also be equal to psi of x plus a. Well, let's see, psi is normalized. I can write this as from minus infinity to infinity dx x plus na, or let's say y plus na times psi of y plus na squared. I'm just redefining x to be y plus na. But the measure is not invariant, so this is minus infinity to infinity dy psi of y plus na squared. This should be 1. But you see, if we shift the wave function by a, we get a multiple of lambda, if it's an eigenstate. If we shift it twice, then we get lambda squared. If we shift it n times, then we get lambda to the n. Lambda to the 2n psi y squared. But psi is properly normalized. So its integral over y just gives me 1. So 1 should be equal to y squared times 1. We can just take n equal to 1. So this tells me that whatever this lambda is, n is 1. I mean, for every n, it should be true. So the magnitude of lambda should be 1. Right, basically it tells me that it should be a complex number. Let's just call it k times a. So psi of x plus a should be equal to e to power I k times a psi of x for some k. And we don't know what are the possible values of k, but it's just a phase. That phase we could have just said delta, or since we have this a over here, in the limit as a goes to 0, we shouldn't have this thing. So it's just e to power k a is a reasonable definition, let's say. But this tells me that psi of k should be equal to e to power I k times x uk times x, where this uk is periodic in A.
How could you say it's IKA instead of IKA squared?
Yeah, fine. Let me just call it e to power I k a squared. Or let me just give it k tilde times a squared. Why not? This is equal to e to power I k tilde a times a. I don't know what k tilde is anyway. So I just rename this thing as k. So it didn't really make any difference.
A is the lattice constant.
But we don't know what k is anyway.
A.
Okay.
Was it the lattice constant?
Sure. But I mean, I don't know what the exponent, what the phase is, phase of lambda is. I can just give it some name, or I can just give it some other unknown times some known. That's kind of arbitrary. But kind of this definition makes this identification easy. So it looks like a plane wave. You see, if we didn't have any potentials, our solution should have been plane waves. It looks like a plane wave, but it's kind of modulated by this periodic function. Our wave functions need not be periodic. They are kind of almost periodic in the sense that if you just translate them, they just acquire a phase. Now, plane waves basically corresponds to the case when a is equal to 0. Or a is equal to, now plane waves is a equal to 0. Now the question is, what are these U's? Now another thing to notice is that k should be between pi over a and minus pi over a. Or you can say from 0 to 2 pi over a, or you can take this symmetric region. Now the reason is this one. You see, psi of k of x, I can write it as e to power I k x uk of x, but this is also e to power I k plus 2 pi n of x times e to power minus 2 pi over a minus I 2 pi over a n of x times u k of x. N can be an arbitrary number. So this has this form, let's say, and this is periodic with period a. So you can just shift this k by 2 pi over a and still get the same function. I mean, let's say this separation over here into a part that gives you the phase times a part that is periodic is not unique. To make it unique, you can just fix a range of k. Or if you want, you can just put some equality sign in one of them. This is called the first Brillouin zone. well, I don't know how to spell it properly. This is the Bernoulli zone. Now let's try to find an equation that U satisfies. What is the equation of U? We know that psi satisfies this equation, minus h bar squared over 2m d squared by dx squared psi k of x plus v of x psi of x. This is equal to e of x, e times psi of x. Now let's take the derivatives of psi. This is equal to ik e to power ikx. Ik times e to power ikx times uk of x plus e to power ik of x times du by dx. And the second derivative, this will be equal to ik squared e to power ik of x uk of x plus ik e to power ik of x uk prime plus e to power ikx uk double prime. This should be, well, if we just put it in our differential equation, what we have is minus h bar squared over 2m times k squared uk. Well, I will be cancelling e to the power ik of x because they are common both on the left and on the right. And the second one is minus k squared uk plus 2ik uk prime plus uk double prime plus v times uk. This is equal to e times uk. This is the equation that we need to solve. And of course now the energy will be a function of k also. Now we have to solve this equation, find possible values of E. Now how would you like to proceed? Remember, UK is periodic. V is periodic, UK is periodic. Well, we can say V is equal to lambda times Dirac delta x minus NA. So that it will be a... Now, for this potential, we should be able to find an explicit solution. Fourier series, not even Fourier transform, because we know that U is periodic. So UK well, let's see. Are there any other symmetries that you know? We can simplify the question a bit. So okay, we know that the potential is translational symmetric, but it has, it is written in this form, it has one more symmetry. It has a mirror symmetry. So the solutions should also satisfy the mirror symmetry. They should either be symmetric or they should be anti-symmetric. So some of the solutions we can write it as a series in sines, some of them as a series in cosines. We don't need to mix the two. So let's look for symmetric or anti-symmetric solutions first? Let's do the anti-symmetric one, it's easier. There is no constant term.
Isn't using sine and cosine you count each lattice point twice? Isn't it better to use the complex?
Why?
After you do the Fourier series, you count twice. But no, you count only the. No, you don't count twice. You only consider the positive side. Consider the negative side. You need the complex number. No,
Well, okay, one thing we could do, okay, you see, sines, we will have here, let's say, sine of, let's write a m sine of m pi over a x, or 2m pi over a x. It is periodic. Now the sine of 2 pi m over a x is e to power I, let's say this is k, q pm. This is pm of x plus e to power minus I pm of x divided by 2y. So this is minus. One is a left-going wave, the other one is a right-going wave. And you can just write our eigenstates as a sum of left-going waves plus the sum of right-going waves. Or you can just write it as only a sum of left-going waves. You can also do that. Or as a sum of only right-going waves. That's also possible. Well, in fact, let's do it that way. Because then we will be making some identifications. We will be calling these left-moving or right-moving electrons eventually. So let's just write it as a m e to power I pm of x, and such that pm times a, translation by a, this should be equal to 2 pi n, 2 pi m, and hence the possible values of pm's, these are equal to 2 pi over a times m. And in fact, psi of x, this is sum over a m e to power I k plus pm of x. It will be easier to write the Schrödinger equation in this notation rather than just separating it. Because in this form, we have h bar squared over 2m k plus pm squared a m sum over m. Now what is v? Do you agree? Maybe a factor of I, a. You see, if you just compare the dimensions, the left-hand side is lambda over the length, because the Dirac delta has a dimension of 1 over its argument. The right-hand side should be also the same. So it's a m times h bar squared over 2m k plus pm plus lambda over a Well, let's just rename these as B, not confused with this lattice spacing. E to power I k plus Pm of x plus lambda over a e to power I Pm of x this should be equal to E times Bm e to power I k plus Pm of x. So we have the equation for the Bm's, sum over m Bm h bar squared over 2m k plus Pm squared times e to power I no. So there's something wrong I did. Okay, this is the V. Okay. Now this equation is not correct. So we have this one, Bm times k plus Pm squared over 2m times e to power I k plus Pm of x. This is the kinetic term. Plus we have the potential term. In the potential term we have the lambda over a sum over L e to power I PL of x. This is the V. And we have sum over m Bm k plus Pm, no, not Bm times e to power I k plus Pm of x. This is psi. This should be equal to E times sum over m Bm e to power I k plus Pm of x. Okay, now this is the correct equation. Now both sides contains the e to power I k of x. So we can just cancel those. And we are left with, let's see, sum over m Bm k plus Pm squared over 2m minus E. I just move the right hand side to the left hand side, that is the first term, plus lambda over a sum over m and L Bm e to the power I Pm plus PL of x. This should be equal to 0. And we are looking for non-trivial solutions of this equation, if there are any. In the first one, I also have the e to the power I Pm of x, right? Now, Pm plus PL, this is equal to Pm plus L from the definition of the P's. So rather than summing over M and L, what we can do is we can just, let's say, insert a sum over, let's say, large N, where this large N is equal to M plus L. Whatever M and L are, this sum is just 1. Because M plus L is some integer, and I'm summing over all N, so N is equal to M plus N for one value of N, so that sum is 1. Now the advantage will be, when I insert that 1, I can change the order of summation. I can do that N summation not first but last. I can just move everything in that N summation. So 0 will be equal to sum over m Bm k plus Pm squared over 2m minus e to power I pm of x plus lambda over a sum over n. But now, using that Kronecker delta, I can carry out one of the m or the L summations. And let's just do the L summation. L summation just tells me that I should replace L with n minus m. But that will just give me sum over m is left. I have bm e to power I p n of x. Or rather than the L summation, let me do the L summation. No, let me do the M summation. Now, what are the limits of the remaining L summation? They're all from minus infinity to infinity, no? Yes. Now let me just rename n to m. So what remains is a summation over m, bm, not bm, e to the power I pmx bm k plus pm squared over 2m minus e plus lambda over a sum over L b of m minus L. This should be 0. But then the coefficient of e to the power I pm of x should be 0. Okay, now the last thing that remains is for which values of E does this equation have non-trivial solution?
Can you say the summation of all of these is some constant?
Well, you see, we didn't fix the normalization. You can fix one constant. So that would be mainly you are saying that let's fix that constant by the requirement that sum over all the b's is just 1. Because if there is one solution, we can just multiply that solution by some constant and it will still be a solution. So you are saying that, let's say, L of B m minus L, let's just fix that to 1. Now the thing okay. Let's fix it to, or minus 1. Or 1, sorry. Then Bm should be equal to minus lambda over A. Remember, this is positive. 1 over K plus Pm squared over 2m minus E. So this is a solution. Pm is m pi over a.
trying to understand whether the summation converges.
So how do we get the energy eigenvalues? We didn't have any constraint on E. Or didn't we? That is a constraint on the possible values of E. So minus lambda over A, sum over L, 1 over K plus P M squared over 2M minus E, they should be equal to 1. This is our eigenvalue equation. E, of course, will be a function of K also. Yok, tamam. Let's go. Now, how do you solve this equation?